You think you understand reality, but what if everything you see, touch and measure is just a shadow of a deeper truth? Quantum mechanics isn't just strange, it's hiding a secret that almost everyone chooses to ignore. Today we're going to peel back the veil and confront the quantum reality beneath the surface of the universe. Welcome! In this lecture we'll dive into the very foundations of quantum physics, challenging the assumptions we take for granted and exploring the ideas that are often overlooked. Together we'll ask, what does quantum theory really reveal about the nature of reality, and why has this truth remained largely ignored? By the end, you may never see the world the same way again. Quantum reality is a world that defies the intuitions we develop from our daily experiences. In the world we inhabit, objects have definite positions, events follow predictable sequences, and cause and effect seem straightforward. We expect that if we throw a ball, it will travel along a certain path. If we turn on a light, it will illuminate a room. But at the quantum level, nature behaves in ways that are almost unimaginable when compared to this familiar reality. Particles can exist in multiple states at once, seemingly occupy many places simultaneously, and can instantaneously influence one another across vast distances. These behaviors are not just theoretical, they have been confirmed through countless experiments. Yet despite the overwhelming evidence, the quantum world remains counterintuitive, challenging the very foundation of what we consider real. One of the most striking aspects of quantum reality is superposition. Unlike objects in our macroscopic world, which have clear, definite properties, quantum particles can exist in a combination of multiple states simultaneously. An electron, for instance, can spin in multiple directions at once until it is observed. This is not a limitation of our measurement tools, it is a fundamental property of the universe. Such phenomena force us to reconsider the classical idea that things must always exist in a single well-defined state. The world at this level is fluid, probabilistic, and full of possibilities rather than certainties. Another phenomenon that highlights the strangeness of quantum reality is entanglement. Particles can become linked in such a way that the state of one instantly affects the state of another, no matter the distance separating them. Einstein famously called this spooky action at a distance, because it seemed to violate the principles of locality that govern everyday experience. Yet experiments repeatedly confirm that entangled particles act in perfect correlation, suggesting that the universe is far more interconnected than classical physics allows us to imagine. The implications are profound. Information can exist in ways that transcend the limits of space and time as we perceive them. Quantum mechanics also challenges our notions of causality and observation. In classical physics, measurement simply records a property that already exists. In the quantum world, the act of observing a particle can actually determine its state. Until measurement occurs, outcomes exist only as probabilities, not realities. This means that reality itself is in some sense shaped by interaction and observation, a concept that feels alien to our everyday intuition, but is undeniably real at the microscopic level. Ultimately, the strangeness of quantum reality serves as a reminder that the universe is far more mysterious than our senses can grasp. Our everyday experience, grounded in certainty and predictability, offers only a small window into the deeper truths of existence. By embracing the peculiarities of the quantum world, we begin to understand that reality is not a fixed, solid structure, but a dynamic, probabilistic, and interconnected tapestry, far richer and stranger than we ever imagined. When we measure something in the physical world, we naturally assume we are observing reality itself. We look at an object, take a reading, or record a value, and we believe that this tells us what truly exists. Yet at the quantum level, this assumption breaks down entirely. What we measure is not necessarily the full story. It is often merely a shadow or an impression of a far deeper, hidden reality. Quantum physics reveals that particles do not possess definite properties independent of observation. Instead, their characteristics such as position, momentum, or spin are fundamentally intertwined with the act of measurement itself. The world we perceive through our instruments and senses is only one aspect of a far more complex underlying reality. This idea becomes clear when we examine experiments like the famous double-slit experiment. When electrons or photons are fired at a barrier with two slits, they create an interference pattern behaving like waves rather than discrete particles. But if we attempt to measure which slit a particle passes through, the interference disappears, and the particle behaves as though it followed a single well-defined path. The very act of measuring changes the outcome. In other words, the reality we observe is shaped by the methods we use to observe it, and what we see is only a partial manifestation of what actually exists. Our measurements are not mere passive reflections, they are active participants in defining the behavior of the quantum world. Another layer of complexity arises from the probabilistic nature of quantum phenomena. Unlike the deterministic systems we encounter in everyday life, the quantum world is governed by probabilities. A particle does not have a fixed position or momentum until it is measured. Instead, it exists in a range of possibilities described by a mathematical construct called the wave function. When we take a measurement, we collapse this wave function into a single outcome, effectively choosing one of many potential realities. This implies that what we measure is not the intrinsic state of the system, but a selected slice of a far richer set of possibilities. Our instruments reveal only the shadow of a far deeper quantum truth. Entanglement further complicates the picture. When particles are entangled, measuring one instantly affects the state of the other, even across vast distances. This means that any single measurement provides only a local, incomplete view of a highly interconnected system. The deeper reality is holistic and non-local, and our isolated observations can never fully capture it. Ultimately, this challenges the very notion of objective reality. The world we measure, the facts we record, and the data we rely upon are all projections, shadows of a profound underlying structure that eludes direct observation. Accepting this requires a radical shift in perspective. To understand the universe, we must go beyond what we see and learn to interpret the subtle signs and probabilities that point to a reality far more intricate and mysterious than our instruments or intuition can directly reveal. What we measure is only the tip of the iceberg, and the quantum truth lies hidden beneath the surface, waiting to be uncovered. In our everyday lives, we rely on classical intuition to navigate the world. Objects have definite positions, time flows predictably, and cause and effect seems almost absolute. If a ball is thrown, it travels along a predictable trajectory. If a glass is pushed off a table, it falls. These experiences shape how we think about reality, giving us a sense of certainty and control. Yet when we delve into the quantum realm, these intuitions collapse. The rules that govern subatomic particles are fundamentally different, and the behaviors we encounter often appear contradictory or even impossible when viewed through the lens of classical logic. At the quantum level, particles do not behave as tiny billiard balls following fixed paths. Instead, they exist in a probabilistic haze where multiple outcomes coexist until observation or interaction occurs. An electron does not have a single definite position. It exists in a cloud of possibilities described mathematically by a wave function. To expect a particle to behave according to classical expectations is to misunderstand the very nature of the quantum world. What seems strange or illogical is in fact consistent within its own rules, a set of rules that classical intuition cannot capture. One of the most striking examples of this failure of intuition is quantum tunneling. In classical physics, a particle encountering a barrier higher than its energy should be stopped completely. In the quantum world, however, particles can and do tunnel through barriers, appearing on the other side as if they had defied the laws of motion. This is not a rare anomaly, it is a fundamental aspect of quantum mechanics that underpins processes such as nuclear fusion in stars. Our intuition, rooted in the macroscopic world, fails to predict or even comprehend such behaviors, highlighting the vast difference between everyday experience and quantum reality. Entanglement is another domain where classical reasoning breaks down. When two particles become entangled, their states are linked instantaneously, regardless of the distance between them. Classical intuition would suggest that information cannot travel faster than the speed of light, yet entangled particles behave as if they share a connection beyond space and time. The very idea that separate entities can remain connected in this way defies common sense, yet it has been repeatedly confirmed through experiments. Accepting this phenomenon requires abandoning classical assumptions and embracing the unfamiliar logic of quantum theory. Even the concept of causality is challenged at the quantum level. Events do not always have a single predictable cause in the traditional sense. Outcomes are probabilistic, and multiple possibilities can coexist simultaneously. Our usual expectations about sequences and predictability become unreliable, forcing us to reconsider the meaning of reality itself. Ultimately, the failure of classical intuition at the quantum level is not a flaw in science, it is a revelation. It teaches us that the universe is far more complex and subtle than everyday experience suggests. By letting go of the comforting assumptions of the macroscopic world, we open ourselves to a deeper understanding of reality, one that is governed by probabilities, entanglement, and possibilities rather than certainty. Classical intuition may fail, but the quantum rules reveal a new, astonishing order beneath the surface of what we thought we knew. Physics as a discipline has made incredible progress in describing the universe, from the motions of planets to the behavior of light. Yet at its very foundations, there are truths that remain overlooked, subtle aspects of reality that challenge the assumptions upon which much of classical and even modern physics has been built. These hidden truths are not merely abstract curiosities, they have the potential to reshape our understanding of the cosmos, forcing us to question what we consider solid, certain, or real. The quantum world in particular is full of phenomena that contradict our conventional expectations and reveal gaps in our understanding. One of the most striking examples is the nature of wave-particle duality. Light and matter can behave both as particles and as waves, depending on the experiment. This dual behavior defies classical categories. In the everyday world, something cannot simultaneously be a wave and a particle. Yet in quantum mechanics, this duality is not an exception, it is fundamental. For decades, physicists debated the meaning of these observations, and even today the full implications of wave-particle duality remain unresolved. This is a truth that quietly challenges the very framework of how we model reality. Another overlooked truth lies in the role of the observer. In classical physics, the world exists independently of observation. Objects have definite properties whether or not anyone measures them. Quantum mechanics shatters this assumption. The act of measurement does not merely reveal a property, it can determine the outcome itself. This implies that reality is not entirely separate from the process of observation, a concept that many physicists initially resisted and that continues to provoke philosophical debate. Ignoring this truth has allowed classical intuition to persist far longer than it should have in understanding the microscopic world. Entanglement, too, represents a profound overlooked truth. Two particles can become linked in such a way that the state of one instantly influences the state of the other, regardless of distance. This phenomenon suggests that information and correlations exist beyond classical spatial and temporal limitations, hinting at a deeper interconnectedness of the universe that traditional physics struggles to accommodate. Many overlooked truths like this reveal that the universe may operate according to principles that are far more holistic and non-local than our standard models assume. Even the uncertainty principle, one of the pillars of quantum mechanics, is often misunderstood or underestimated in its implications. It tells us that there are fundamental limits to what can be known about certain pairs of properties, such as position and momentum. This is not a limitation of technology or experiment. It is a statement about the nature of reality itself. The universe is inherently probabilistic at its core, and attempting to impose certainty where none exists can obscure these truths. Ultimately, these overlooked aspects of physics serve as a reminder that the universe is far richer and stranger than our conventional theories suggest. The assumptions we take for granted, the categories we use, and the intuitions we trust can all be challenged by subtle phenomena that reveal a more intricate, probabilistic, and interconnected cosmos. By paying attention to these overlooked truths, we gain the opportunity to expand not only our scientific knowledge but also our understanding of reality itself, learning to see the universe as it truly is, beyond the comforting illusions of classical intuition. One of the most astonishing revelations of quantum mechanics is that observation is not a passive act. It can actively influence the nature of reality itself. In the classical world, we tend to think of measurement as a neutral process. We look at a clock to see the time, measure the temperature in a room, or weigh an object, all without changing the underlying reality. At the quantum level, however, this assumption no longer holds. The very act of observing a particle can determine its properties, its behavior, and sometimes even its existence in a particular state. Reality, it seems, is not fully formed until it is observed. This idea is most clearly illustrated by the double-slit experiment. When particles like electrons or photons pass through two slits, they produce an interference pattern, characteristic of waves, suggesting that each particle passes through both slits simultaneously in a superposition of states. Yet, when a measurement device is used to determine which slit a particle passes through, this interference pattern disappears, and the particle behaves as though it passed through only one slit. The mere act of observation collapses the wave of possibilities into a single definite outcome. What we see, therefore, is not simply an underlying reality, but a version of reality shaped by our interaction with it. This influence of observation extends far beyond a single particle or a single experiment. It challenges the classical idea of an objective, observer-independent reality. In the quantum world, properties such as position, momentum, and spin are not intrinsic features that exist regardless of measurement. They are relational and contextual. Until we measure them, they exist in a probabilistic haze described mathematically by a wave function. By observing, we select one possibility from many, effectively participating in the unfolding of reality itself. Entanglement amplifies this phenomenon in even more dramatic ways. When two particles become entangled, measuring one instantly influences the state of the other, no matter the distance between them. Observation in one location can have immediate consequences for a distant system, demonstrating that measurement is not just a local effect. It can reach across space to shape outcomes elsewhere. This suggests a level of interconnectedness in the universe that defies our everyday intuitions and classical assumptions. The implications of observation shaping reality are profound. It forces us to reconsider the role of consciousness, interaction, and measurement in the cosmos. It implies that the universe is not a static backdrop against which events unfold, but a dynamic, participatory system in which observers and observed are intertwined. The reality we experience is, in part, a reflection of our engagement with it, highlighting the subtle and often overlooked role that interaction plays in the formation of the physical world. Ultimately, understanding that observation can influence reality compels us to look beyond the surface of things, to recognize that what we measure is never the whole story. It reminds us that the universe is more fluid, mysterious, and participatory than we might have imagined. The act of observing is not merely recording the world, it is helping to create it, shaping the quantum fabric that underlies everything we perceive. Quantum mechanics is more than just a set of equations or experimental results. It is a window into the deepest truths of the universe. When we study it, we are not merely learning about electrons, photons, or atomic nuclei, we are learning about the very nature of reality itself. The principles of quantum mechanics challenge the assumptions that underpin our everyday thinking, forcing us to reconsider what we mean by existence, causality, and the very fabric of the cosmos. By grappling with these ideas, we begin to see the universe in a fundamentally different light, one that is far stranger, more subtle, and more interconnected than classical physics ever allowed us to imagine. At the heart of this transformation is the realization that certainty is often an illusion. Classical physics gives us the comforting sense that the world is predictable and objective, but quantum mechanics replaces this with probabilities, superpositions, and uncertainty. Particles do not have fixed properties independent of observation, and outcomes are not predetermined. They exist as possibilities until they are measured. This shift in perspective teaches us that the universe is not a static machine operating according to fixed laws, but a dynamic system in which potentialities play as important a role as actualities. Reality is not just what happens, it is a landscape of possibilities that unfolds in surprising and often counterintuitive ways. Quantum mechanics also reshapes our understanding of space and time. Entanglement shows us that distant objects can be connected in ways that defy classical limitations, suggesting that the universe is deeply interconnected at a fundamental level. This interconnectivity challenges the notion of independent, isolated systems, and encourages a view of reality in which relationships and correlations are central. The universe, in this sense, is less like a collection of separate parts and more like a web of interactions, where the state of one entity is linked to the states of many others, sometimes across vast distances. Moreover, understanding quantum mechanics forces us to rethink the role of the observer. In classical physics, the observer is largely irrelevant. The world exists independently of who is watching. In quantum mechanics, observation is an active process that can shape outcomes and bring possibilities into reality. This does not necessarily require consciousness in the human sense, but it does highlight that the act of interaction matters. The universe is participatory, and our models of reality must account for the subtle ways in which measurement and interaction influence the phenomena we study. Finally, embracing the lessons of quantum mechanics encourages intellectual humility. It reminds us that our intuitions, shaped by a macroscopic world of solid objects and predictable events, are often inadequate when confronted with the fundamental workings of the universe. By expanding our thinking beyond classical assumptions, we open ourselves to a universe that is more astonishing, more complex, and more beautiful than we ever imagined. In the end, understanding quantum mechanics does not merely add knowledge, it transforms our worldview. It reshapes how we conceive of matter, energy, space, time, and the relationship between observer and observed. It invites us to explore the universe not as passive spectators, but as participants in a vast, intricate, and ever-unfolding cosmic reality. By seeing through the lens of quantum mechanics, we gain a deeper appreciation of the profound mystery and elegance that underlies everything we experience. As we reach the end of this journey, one truth becomes clear: the universe is far stranger, richer, and more mysterious than our everyday experience would suggest. The quantum world challenges everything we take for granted: our intuitions, our assumptions about cause and effect, and even our very notions of reality. What we measure is only a shadow of a deeper truth. Observation shapes the outcomes we see, and classical logic often fails to describe the behavior of matter and energy at its most fundamental level. Yet it is precisely in these strange and counterintuitive principles that the beauty of the cosmos is revealed. Quantum mechanics does not merely describe particles or forces, it transforms our understanding of existence itself. It shows us a universe of possibilities, probabilities, and profound interconnections, where what seems isolated may be intimately linked, and where reality is as much a dynamic interplay of observation and interaction as it is a fixed set of facts. By confronting these truths, we are invited to step beyond the comfort of certainty and embrace a deeper, more nuanced understanding of the world. Ultimately, the quantum truths that are so often ignored are not distant abstractions, they are the foundation upon which everything is built. From the behavior of atoms to the workings of the cosmos, the quantum world shapes the reality we inhabit, even if we rarely notice it. Recognizing and contemplating these hidden principles allows us not only to advance our scientific knowledge, but also to cultivate a sense of wonder, curiosity, and humility about the universe we live in. So as you leave this lecture, remember that reality is far more intricate and mysterious than it appears on the surface. The quantum world invites us to look deeper, to question assumptions, and to appreciate the subtle, interconnected, and often surprising nature of existence. By acknowledging the truths that are often ignored, we begin to see the universe not just as it seems, but as it truly is, a place of infinite possibility, profound complexity, and breathtaking wonder.